Hello everyone. My name is Shiva Sriram, and today I'll be presenting my project titled Drug Substitution Recommendation System using Machine Learning. So, this project focuses on building a data-driven system to help identify safer alternatives for drugs based on real-world adverse reactions data. So, that's my project, and we'll move on to the introduction slide. So, as we all know, medication safety is a critical concern worldwide. So millions of people take prescriptions and over-the-counter drugs every day, and unfortunately, adverse drug reactions account for thousands of hospitalizations each year. So our goal is to use machine learning to recommend safer drug alternatives and ultimately improve patient outcomes. So why predict safer drugs? As I said, predicting safer drugs is important because it empowers both doctors and patients to make more informed choices. So we'll move on to the next slide, which is our research goals. Our research goals are to group similar drugs based on their side effects and warnings, and then study the safety profile of each drugs, and then build a system that recommends safer alternatives. And finally, to help patients and doctors choose better options to reduce the chance of harmful reactions. So we'll move on to our next slide, which is an overview for the data set. So we got this data from a website called OpenFDA, Open Federal Drug Administration's website. So using API call, we got the data, and the main features of this particular data sets are active ingredients for each drugs, warnings uh, for the drugs, and then their adverse reaction, and then finally risk cost. So these are some main features that we used, and then we cleaned over 100,000 plus drug entries. So this is a big data set. And this is a snapshot of the raw data. So, this particular data set, it had so many missing values and inconsistent values. So, as you can clearly see under the drug name, we have so many unknown values, and even under warnings, we have, so many drugs which had warnings listed as nil NA. So this is my data set before cleaning, and then we'll move on to the next slide, which has the snapshot of the clean data. So here, we encoded the data, and then, we converted, all the data, and then we kept only the features which are very important. As you can clearly see, we have patient age, warning length, risk score, and then all these other important features which helps us to classify or, predict safer drugs. We move on to the next slide. So which covers the supervised learning methods that we used in this project. So we used naive Bayes classifier, decision trees, logistics regressions. So each model brought its own strength, and we tested them individually, and then we compared to find which model worked well for our project. So this is the next slide covers the unsupervised learning methods that we used in this project. So we used principal component analysis PCA to reduce the number of features while keeping most of the information. And then clustering algorithms like k-means, TB-scan, hierarchical clustering to group similar drugs. And then finally, some association rule mining to discover hidden patterns in how side effects occur together. So the next slide covers the key findings for the first supervised learning algorithm, naive Bayes. So we found that the multinomial naive Bayes delivered the best overall performance in terms of accuracy and reliability. And then, all naive Bayes models were effective in distinguishing between safe and unsafe, but out of the three, multinomial was the best. We move on to the next slide, which covers the key findings from decision trees. So here, uh, the decision tree using Gini index achieved perfect accuracy. However, when we limited the tree's depth, the ability to correctly classify unsafe drugs dropped, showing the importance of using, a rich set of features. I mean, a lot of features. apparently, there are so many features that were important in order to classify, in order to classify whether a particular drug is safe or not. So we'll move on to the third supervised learning method, which is logistic regression, and we compared it with multinomial naive Bayes too. So as you can clearly see, logistic regression achieved a perfect classification performance compared to the multinomial naive Bayes. It had a slightly better precision, and then fewer false positives, so making it the most reliable model for binary classification. And then we'll move on to the unsupervised techniques. So the first one is principal component analysis, PCA. So through PCA, we discovered that only few components captured most of the variance in the data set. So this dimensionality reduction made clustering more effective, uh, without losing critical information. So as you can clearly see in this graph, risk score was one of the most important feature, followed by warning length, reaction drug, hypersensitivity, reaction dysplasia, and then reaction nausea. So these are different reactions basically for the drugs. And these are the top 5 principal components that we got. And moving on, we'll go to the clustering uh, unsupervised technique. So using k-means clustering, we grouped drugs into clusters based on the features, which allowed us to recommend safer alternatives. From the same cluster, if a particular drug is classified as, as this allowed us to recommend safer alternatives from the same cluster if a risky drug was identified. So clearly see we did TB scan as well. We did hierarchical clustering, but out of these three, I felt clustering with k is equal to two clusters gave us the best output, best result. So it was fast, scalable, and it clearly separated the group based on the risk. And yeah, we got a great model. So we'll move on to the final unsupervised technique that we used, which is association rule mining, ARM. So high risk warnings are combined with adverse reactions are it's often pointed out to unsafe drugs. So this helped reinforce the need to recommend uh, safer alternatives based on the side effect patterns, of course. So this is the slide for ARM. So we'll go to the overall final conclusion. So to summarize, so what we did, data-driven safety, which is machine learning models provide a structured way to evaluate the drug risk. We classified whether a drug is safe or not. So we use supervised learning to do that. And then the healthcare applications. I mean, these models can help pharmacists and doctors to offer safer alternatives. And then the explainability concept. So the decision trees and logistic regression allowed for easy interpretation. Which is important, in critical, and also critical in medical settings. So they have to understand what they're doing. So and then for better grouping, we used clustering. So clustering ensure that the recommendation stayed within the context relevant drug data groups. And the final takeaway is basically, rather than just identifying a risky drug, our system actually supports safer treatment decisions for better patient care. So this is the overall conclusion. And then finally, you know, uh, to conclude what we did, we can also say, uh, in this presentation, we first explored the supervised learning models, and then we use, which we use to predict whether the drug is safe or not. And then we looked at unsupervised methods like clustering and PCA, which helps us to group similar drugs together based on the safety profiles. Together, both using these both approaches, it allowed us to achieve the final goal of the project, which is to recommend a safer drug alternative. how do we do that? So by achieving or by identifying high risk drugs and then suggesting similar lower risk options from the same cluster. So moving forward, this project has a scope. The next step would be probably to build a simple web-based tool that takes drug as an input and it will return a safer alternative in real time. So this could be used by pharmacists or even integrated into hospital systems to promote safe prescribing of medicines, drugs. So yeah, thank you.